Hello, Alexander. Welcome back for another exciting edition of Physics Problems. So, this one we are going to do problem 9, zero force point between two planets. And we're going to use Newton's universal law of gravitation. And it has been since superseded by Einstein's theory of relativity, but it's still good at giving us approximations, answers in most situations. So that formula, that law is F equals G times M1 over M2 over R squared, or so let's understand what this is the force. These are masses, the masses of the two objects. So between these two masses, there's going to be a gravitational force of attraction between the two. Any two masses have this. It's just if the objects are not that massive, or the distances are very great, that the force is not that much. So these two masses are going to exert a force on each other. So M1 will enact a force on M2, and M2 will act a force on M1. And it'll be an equal to in magnitude to this number that we calculate here. It's just they'll be in opposite directions, force pairs, back to Newton's force pairs. So Newton's third law. So M1 is going to act on M2, and M2 is going to act on M1. Both of those numbers will be equal in magnitude to this force that we calculate. It's just they'll be in opposite directions. This is the distance between the two objects, and you got to square it. Distance between objects. Now, what's this G? Well, this G is kind of a fudge factor. It's like, hey, I found this great relationship, but I have to multiply by something. Okay, well, we'll just multiply by this G. We'll just figure out this value and boom, put it in there and my equation's golden. So all it is makes this equation work. It's a constant, kind of like the ideal gas constant that we used in physics last unit. So what is this G? In fact, you're going to find it's not incredibly important in this problem, not important at all, but we might as well write it down to be thorough. And it is approximately 6.673 times 10 to the 11th, negative 11th, sorry, to the negative 11th, and the units are newtons, meters squared over kilograms squared. Say what? What units are on there? Well, just like the number fudging this thing to work, we wanted the units to work out. At least that's how I interpreted. So all of these units and this number make this equation. All the units play nice and everything is good and happy and spits out the number that we want. Okay, but I said that it wasn't important. Well, you'll see here in a minute. First, we need a picture. Okay, we got the sun. Ooh, why don't we use orange. Yellow is nice, but we use orange here. Sun, beautiful sun, we spin around you. Yeah, that's a little bubble guppies for my children. So we have the sun there. We'll do planet Earth here. Ooh, where are we? There we are. Planet Earth. Not to scale, people, not to scale. So the Earth would be way tinier and way, way further out. But that's a whole nother lesson. So we're going to call this approximately 1.50 times 10 to the 11th meters. You may be used to it as 93 million miles, or it takes about 8 to 9 minutes for light, any type of radiation from the sun to reach us. That's about 93 million miles, but we're in meters, which is nice, so we don't have to convert. Now we have some point. We can call this point right here. I'm going to put this point here. Some point. It's going to where the force is equal. Well, since the sun is way, way more massive, in order for the pull of the sun on the object and the earth on the object to be the same, you have to be way, way closer. I'm not even going to put it how close you have to be. I'm just going to put it right here so we can see the two. So it's got to be way closer to Earth, way closer than that, as you're going to find out when the calculation's done. And we're going to call this distance x. Well, what is this distance between the object? It could be a satellite, it could be whatever you want it to be. And then this will be 1.50 times 10 to the 11th minus x is this distance, because this distance is 1.5 times 10 to the 11th, and then this distance here would be 1.5 times 10 to the 11th minus x, and x is this distance right here. And actually this distance is the distance we're going to actually ask for the answer, but we'll come back to that. Okay, so we need to set up this thing here. So we have this equation actually twice. So we want the f, and we'll call this object OBJ. So the f of the sun on the object is equal to g m of the sun, m of the object over the distance between the two. We'll call it R1 squared. That's got to be equal to f of the earth, the earth on the object, and that's g, it's a constant, m of the earth, m of the object all over the distance between those. We'll call it R2 squared. Before we get started, let's make our lives a little easier, because this is going to be algebraically not a mess, but it's going to have a little bit of algebraic hurdles to jump. These cancel because they're the same in both problems. How about the mass of the object? We want mass of the object cancels out. So we're left with this mass of the sun over the distance between the object and the sun, and the mass of the earth over the distance between the earth and the object right there. So we made our lives quite a bit easier by doing that. And these two why are these two set equal to each other? Because that's what the problem's asking. Calculate the point between Earth and the sun at which the object is zero net gravitational force. So basically the sun's pull this way will equal the Earth's pull that way. Alright, there we go. So and that's why I set this up. So at this point, it just becomes a work of algebraic strength here. Let's use purple. We haven't done that yet. The mass of the sun, which is given to us in the problem as 1.991 times 10 to the 30th. Excuse me. Over the distance, which we called 1.5 times 10 to the 11th minus x, and we got to square that, equals 5.98 times 10 to the 24th. That is the mass of the Earth over the distance between the object and x there. Okay, well, here is my suggestion. You could multiply this over here, that over there, you got a quadratic and have all that fun with that, but we can make our algebraic lives a little bit easier by taking the square root of both total sides first. Well, if you recall, if you take the square root of this whole thing, it's a fraction, you can take the square root of the top, the square root of the bottom, square root of the top over the square root of the bottom. And yes, there's a subtractance sign in there, and that usually is like, oh, no, warning, you can't, that's going to cause other issues. Well, it's all wrapped up in this parentheses, because we're taking the square root of this, and since it all is there, when you take the square root of the bottom, well, you're just getting rid of that squared there with the square root of the bottom. So the bottom is not, does not hurt us to do that, so it works out nice. So I've already taken the square root of this, and if I can track down my numbers, 1.411 times 10 to the 15th over, and then the square root of this is just that, 1.5, I'm going to leave it in parentheses though, times 10 to the 11th minus x. Oh, there we go. No squared though. That's how the square root got rid of it. So undid it. Opposite operation. Now the top over here was 2.445 times 10 up to the 12th all over x squared, not squared, you undid that in there. So now we just have this proportion here. You multiply this x over here to this side, it cancels out, you multiply this and distribute. This has to be distributed to both of those. And when you come up here, and so we're going to come up here, and we're going to, okay, we're now up here, and we would be left with 1.411 times 10 to the 15th x equals 3.66 times 10 to the 23rd minus 2.44 times 10 to the 12th x. Sorry, it's messy. So there's an x term and there's an x term. So you add this over here and then you divide both sides by this coefficient. So you end up with an x equal to 2, lost in my own scribbles here. I have it somewhere. 2, 5, 9, 5. And then I will round, and it looks like it is 5. Oh, 1, 2, 3, 4, 5, 6, 7, 8. Yes, so it's 2.595 times 10 to the 8th meters is this distance. So that's this distance right there. Yay! But the problem wants this. So you have to subtract that off 1.5 times 10 to the 11th. Well, this is times 10 to the 8th, so this is really kind of small compared to this times 10 to the 11th, but we'll go through this step anyways. 1.5 times 10 to the 11th minus our answer here, which is 2.595 times 10 to the 8th. Well, that gets us 1.497 times 10 to the 11th meters away from the sun. If you look at this, look how close that is to Earth. So this is 1.5, so it's really, really close to this, 1.497 meters of the, or 1.497 times 10 to the 11th meters out of 1.50 times 10 to the 11th meters is the, it's because the mass of the sun is way, 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 way higher. So, could you have just put in this number? Depends on the tolerances of the problem and how close they wanted to get you, wanted you to get to. So, hope this helps. Let me know. Thanks.